get this party started, yeah? Hello. There we go. Got it. Okay. How is everyone today? Hey, JTS, my friend. All right. We're gonna wait a few minutes, of course, so everybody can start making their way in. Just to spread. Wait. Oh, yeah. Okay. I'm good, my dude. I'm good. Sitting and chilling, having a nice time. Be taking a small trip out for the weekend, so should be pretty nice. I haven't been out on a trip in a while, so figured you might as well see my cousin and stuff. Yeah. You're currently searching internships for your major. JTS, what was your major again? Off the top of my head, I forgot. Horticulture? Hmm. Be a good internship for horticulture. Hmm. Plant scientists. Uh, hmm. Well, if they have a position available even at this time, you could always try the U.S. Parks and Recreational Services. I'm pretty sure that they're always looking for more arborists to actually study up on the parks there. I'm pretty sure an internship there could take you a long way. I guess that's the one place that I could certainly think. Um, let's see. uh, let's see. The Food and Drug Administration would be another place. They'll need plant scientists to, of course, determine, like, for example, if you bring plants in from overseas and you want to study its effects, for example, like on see if it's an invasive species or not, something like that, then definitely something that could certainly be possible. That's what I can think off the top of my head right now. The Parks and Rec services definitely do a lot of environmental stuff. So environmental agencies definitely require, plant scientists of some variety. Maybe even heck, even the EPA. They need like scientists, for example, to do environmental studies before, say, like building a road. You can't just build a road anywhere. You have to do environmental studies before you build the road. Because what if you're like saying, "Oh, I'm building the road through this wetland." All right, you have to figure out, is it possible to even build a road through the wetland, and what's even in the wetland, and are there things that need to be protected within the wetland? In which case then you don't even have the project in the first place. So, thing is, those things matter quite a bit. So to kind of preserve the ecology of the region. So definitely, there's places where a horticulturist is certainly can fit into just a job that certainly can slot into. So most definitely. All right. We'll wait another minute or so, and then we'll get started here. So we'll get started here with some newer material today. Wahaha. Hey, we're posting the last class to YouTube. Um, oh, okay. Yeah. So Sarah, if you, that's okay. JTS. So Sarah, the answer to your question is, yeah, I should be posting that fairly soon. Yeah, I usually do that 24 hours after the class, but I know sometimes I'll take a day or two, so I do apologize about that. Just a lot on my plate, to be perfectly honest. But if you want to go see it right away, it's here on Twitch. Actually, if you look up my videos here, you'll see a replay of the last class that we had there, Sarah, and that stays up here on Twitch for 14 days. So if you don't see it on YouTube right away, I'm using YouTube as kind of an archive. But if you want to see replays right away, even right after I'm done, it's posted right here to Twitch for 14 days. So yeah, definitely use that if you don't see it on YouTube. No, no, no. No, you're pointing out the right thing there, Sarah. I don't got a problem with that. I just want to give you as many outs as possible. So you should be able to see the previous stream as much as this stream. So this stream will be available right after we're done here today. And again, that'll be up for 14 days. So 2 weeks is plenty of time. And then if you miss anything, the past 2 weeks, then you got the archive there to help you as well. So I just wanted two ways you can see a replay in a short period of time, or if a longer period of time, it is what it is. Okay. All right. I think we're okay here. And there we go. All right. That's what I was looking for. All right. All right. Let's go ahead and get started here. All right. So, okay, let's get started with today. Welcome back to Thursday, end of the week time today. So today, all right, we are going to be moving forward here from where we left off last time. Last time, we finished up talking about quadratic functions and talked about vertices, right, and how to draw a parabola. At the end of last time, we also talked about polynomials, and we discussed here what a polynomial is, what a degree of polynomial is, and what the leading coefficient of a polynomial is. So today we're starting still within section 3.2, but we're going to discuss more in detail about polynomials and what we can get from them. The first thing that we're going to talk about here is going to be question number 4, and that asks, what is the leading coefficient test? Okay, so the leading coefficient test specifically, let me change that font, there you go, good job. All right, so the leading coefficient test is going to determine the graph behavior at the ends of the graph. So this test determines the end behavior of a graph of a polynomial. Okay. So what we're going to have happen here is, since we're looking at polynomials, all right, we are going to have two specific cases. Now, remember how it goes here. If you have the first term, let's say leading coefficient, okay, that's the very first number in front of the very highest degree term. So to simply put here, how do we know what the end behavior of the graph is going to be? Well, let's take a look and see what we have. So we're going to have two cases here. So let me bring up the paint tool here. All right, that is a very small canvas. Make that stupid big. There we go. Okay. So the first thing we're going to look at here is what happens if the degree is even. Okay, so let's say the degree is even. So let's say the degree is 2, 4, 6, 8, okay, whatever. All right, and let's say the leading coefficient leading coefficient is going to be bigger than 0. Now, just for the sake of use, I'll just label this as LC for leading coefficient. Yeah, just so I don't want to write that in all the time. So if the leading coefficient is positive and the degree is even, then this graph will open up on both sides. So basically it'll go like this. It'll go up. It'll have some graph in between, blah, 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 and then it'll go up. So on both sides of the ends of the graph, it'll go up just like so. If you flip it around, and let's say the leading coefficient here is negative, then it's going to go down. So it just flips over there, random graph, and then it goes down. So this is basically what the graph will look like. Essentially, some random graph here in the middle, but you know for a fact that the ends of the graph are going to go down if the leading coefficient is negative. Now, in this case here, let's talk about if the degree is odd. So if the degree is odd, let's say our leading coefficient here happens to be positive. So again, degree being odd means that the degree is 3, it's 5, it's 1, it's 3, it's 5, it's 7, okay, whatever the case may be. And we want to determine, we say, okay, well, what happens if the leading coefficient is positive? Well, it turns out that basically the graph kind of goes like this. It goes down, and you have some random graph in between, and then it goes up. Okay. So that is if the leading coefficient here is positive. Finally, if the leading coefficient is negative, so if the leading coefficient here is negative, then flip it around, and what you'll get is you'll have it go up, random graph, and then go down. So this is the end graph, the end behavior for the graph based on the leading coefficient of the polynomial. All right, are there any questions about that? So the best way to kind of put this out, just to make it as easy as possible, all right, so if you're not sure which way it goes and you're like, I don't know, a good way is to determine this would be like x squared, this would be like negative x squared, this would be like x cubed, and negative x cubed. So those are the easiest examples. Degree is even, positive coefficient. Degree is even, negative coefficient. Positive coefficient, negative coefficient. You get the idea. Okay. In any case, those are some basic examples if you want to kind of visualize in your head what the end graph behavior is going to look like. Alrighty. Okay, no questions from you guys. All right, good. Okay, let's talk about the next one here. What is the multiplicity of zeros in a polynomial? Okay, so the multiplicity of zeros in a polynomial, basically the definition of multiplicity are how many times the zero occurs in the polynomial. Okay, so how many times the 0 occurs in the polynomial? Let's do some examples, okay? So I think an example certainly is well worthwhile here. So let's give it a try. Now for this one here, I'm gonna bring out my math type dude. Okay. Okay, so let's say our polynomial is given to us like this. Let's say we're given f of x here is equal to, let's call it, I don't know, x minus 1, and then we'll go with x plus 3, and go with one more here. Go with x minus 7, sure. Okay, so I just randomly made stuff up here. It is what it is. I probably should make that smaller. Yeah, let me make that smaller. There we go, it's better. Okay. Okay, so first and foremost here, we have x minus 1, x plus 3, x minus 7. So we've effectively, what we've done here is we have gone ahead and we have factored out. So we're making the assumption here this is all factored out, it's all nice and pretty, no problem. Now the question is that what are the zeros and what are their multiplicities? Okay, so let's do our example here. So first of all, oh, that's pretty nice of that. All right, that's actually good for the ones. Let's talk about the zeros here. What are the zeros of this polynomial? What are the zeros of this polynomial? We have x minus 1. Okay, so 1 minus 3 and 7 is correct. Very good. So 1 minus 3 and 7. Okay, so definitely true. Now what we want to determine is the multiplicity of each one of those zeros. Okay, so it says, well, how many times does that 0 occur in the polynomial? All right, well, let's take a look. How many times does 1 appear as a 0 in the polynomial? What would be our multiplicity here? Once. That's correct. Now you're probably saying, now I can understand the multiplicity is 1. All right, so for that one. But I can understand where most of you are coming from here. You're probably saying, time out, time out, time out. How do I know that the multiplicity is 1 specifically? All right, how do I know that? Okay, so that question is very, very valid, and there is definitely a way to determine the multiplicity here. What we're going to look at here specifically, and this is going to be, I suppose, the key here that I'll have to write out here. So the big key here in this case is going to be to look at the powers of every factor to determine multiplicity. So what does that mean in this case? That means if I go back to our original function, this is nice and factored out for us, no problem. But another way to say writing x minus 1 would be, say, x minus 1 to the first power. I can do the same thing with x plus 3, and I could do the same thing with x minus 7. They're all to the first power. So what that means is that essentially 1 occurs once, so that multiplicity is 1. Minus 3 occurs once, so that multiplicity is also 1. And 7 also is a multiplicity of 1. So each factor only occurred one time because of the power of each of the respective factors. So if you need to rewrite it with the 1 as the exponent, then you can go ahead and do that. And then that way, you can clearly see what the multiplicity is going to be. Now, let's try another example, because I think another example certainly is in the cards. So, because some of these can be a bit tricky, so here is I always like to throw some curveballs, so let's figure this out here. All right. Yeah. Okay. So let's look at this example here. All right. So my question is, of course, we need to first, let's state the zeros that we have here. Okay. So in this case here, what are our zeros? What are zeros for this? 0, 1/2, and 7. Okay, very good. So we got 0, make a little space, 1/2, and 7. All right, fair enough. So don't forget here, this x squared still factors as one of our zeros, okay? So don't forget to not drop that out. That x is going to be there, so that's fine. Well, what's our multiplicity for 0? That's correct. The multiplicity here is 2, right? We see x squared there. So that means that 0 occurs 2 times in the polynomial. So x squared meaning a multiplicity of 2. How about 1/2? Okay, that's right. Multiplicity of 3. That's right. Right, because we have 2x minus 1 to the third power. So that means our multiplicity is 3. And how about 7? 1. Good. All right. Okay, so we have that. All right, any questions about multiplicity here so far? All right, so if there are no questions here, we'll go ahead and move forward. Okay. Would the multiplicity of the whole function be the 3 added up? No. Actually, that's not true. The degree would be all the multiplicities added up, but not the multiplicity as a whole. Multiplicity is for each individual 0. If we're talking degree, yeah, you can combine all that together. That's fine. Any other questions? Okay, let's go ahead and take a look here, and we're going to now use multiplicity. So let's look at question 6. What does multiplicity mean in terms of the graph of a polynomial? All right, so multiplicity has basically 3 categories, 3 meanings. And I split up one into 2 different meanings because it's a lot easier to understand. So let's go ahead and put it together, and let's see how this works out. Okay, the first one here is the first case is going to be a multiplicity of 1. So what's the graph behavior at the multiplicity of 1? So in this case here, the graph will cut through the 0, will cut through at the 0. So what does that mean? The graph will cut through at the 0, all right, or cross through at the 0. I'll say cut through, I guess. So let's take a look at what that means based on a picture. More in there. Um, oh, let's get rid of this here. And this. Okay. All right, so we'll get to that eventually. So this is what crossing means. Let's say this is the 0 here, for example. Well, in a sense, with the multiplicity of 1, it cuts through just like this, all right? Or it will also, again, it will cut through just like this. So it could come down and then could cut through the 0. So just like that. So I would put like these pictures here next to this. I wonder if I could, oh, why did I do that? Let's see if I can crop these if possible. Oh, maybe not. Well, let's copy pasta, see if that works. Hey, that works. All right. I like that. All right. There we go. So the graph will cut through at the 0. Here you go. Now you got it. So that's what would be the graph behavior at those zeros. Okay. Now, let's look at the next possibility. What happens if the multiplicity is even? Okay. So what happens if the multiplicity is even? So we're talking, again, 2, 4, 6, 8, okay, those kind of multiplicities. All right, what happens to the graph at those particular zeros if they have an even multiplicity? Well, it turns out in this case here, the graph will touch the 0, but will not cross. So what does that look like as a picture? Let's go back to our pictures here. So basically this is what it's going to look like. Here is our 0, and it could come down from here. It could touch that 0 and then make its way back up, something like that. And then we'll have a 0 here, and again it could touch that 0, goes up, touches it, and then say comes back down in some capacity. So this is what we have for the multiplicity being even. Go move that down there. Okay, so that's the second case there with the multiplicities. And we do have one more case here, so let's go ahead and do that. Okay, so the last one here is if the multiplicity is odd but not 1. Okay, so specifically we're talking 3, 5, 7, 9, okay, those guys. So we're not including 1 as part of this because 1 I like to separate out as its own behavior compared to all the other odds. So let's talk about what happens to this. So what happens here with the graph is that the graph will wiggle through the 0. So what do I mean by wiggling? Well, let's take a look. So I'm just going to go ahead and delete this. Can I delete this? Sure. All right. So what does wiggling mean? Here's the 0. And what it'll do is it'll kind of come up here, and then it kind of flattens out a little bit, kind of wiggles through, and then it finally goes through just like that. So it doesn't quite cut. There's like kind of a flatness in the middle there, like kind of like x to the third there. So here it's again, you could come the opposite way. You come down toward the 0, you kind of wiggle through, and then finally you make your way down just like that. So these are essentially two ways that we can describe, let's say the wiggling part there. Okay. There we go. All right. So multiplicity odd, but not 1. The graph will wiggle through the 0, just like so. Okay. All right. Any questions about that so far? No? Okay. Okay. So the multiplicity can be 112 and still just touch because it's even. Same with odd. Yeah. So if the multiplicity is 112, yeah, you're absolutely right, GTS. It'll just touch and go back, whichever way that is. Same with odd, it'll wiggle through even if it's 113. So absolutely right. That's why I kind of separate. Yeah, that's why I separate 1 from the other odds, because 1 is just more unique than the other odds. So no problem. Okay. Which one do I want to do? Okay, do that. Okay, let's look at number 7. All right. So number 7 says, what other information will you need to make sure you graph the polynomial? Okay. So in number 7, we're going to be answering the question here, how we can graph a polynomial using certain bits and pieces of information that we've talked about here so far. So what's the first bit of information that we'll need to do? Let's talk about the steps here at the very least. And these steps here are, you can change a few steps around technically, but let's talk about it. First of all, you want to actually have a predictive way that this graph may look like on a very generic level, meaning to say you can use the leading coefficient test to get the end behavior for the graph. So this gives you a good idea about what to expect from this graph here. Okay, that's certainly possible. All right. Step 2 is basically to determine the zeros and their multiplicities. Okay, so lose the leading coefficient test. We know that what it looks like here. We're going to determine the zeros and their particular multiplicities. And then, of course, we're going to find, we're going to say, using our calculator, we will find additional points such as maximum or minimum points. Okay, so we can establish a pattern here using the calculator that could be very helpful for us in this circumstance. Okay, so because If we wanted to do this by hand, it would take quite a while, especially with graph behavior kind of going all over the place. That can be a bit of a pain. All right. Now, one thing that you get from the zeros here, by the way, is you get those x-intercepts. So that's what makes it very convenient. Okay. So let's go ahead and do a couple of examples here. Let's go ahead and see how we can graph this, and again, see what we're working with. All right. Let's start off with something nice and easy, and we'll work our way up. How old am I, and are you a real professor? The answer to the second question is yes. The answer to the first question is 41, which that was 4 days ago. Yeah. No, people don't believe me when I say 41. I look like I'm in the 30s, but I'm like, oh no, I'm really 41. I swear. I don't know if that's a badge of honor or not. Meh. That's cool. Thank you. I appreciate that. I just had a nice time with the family. I hadn't seen them in a while. Hadn't had a chance to talk with them, so it was good. All right. Here's our uh, function here. So x to the fourth minus 6x to the third plus 9x squared. Okay. So let's go ahead and determine, at least going through the steps here. Is there a secret to my youth? Absolutely yes. There's a definite secret to my youth. Actually, 2 steps. Number 1, inherit the genetic gene of baldness. Alright, that way you hold in your youth away from your hair. Secondly, and most importantly, you just have to fart a lot. That's very important, alright? Scratching does nothing, but farting, let me tell you, it works wonders at the end of the day, alright? If your apartment stinks like all hell, then you've done a good job, alright? You have a boyfriend or girlfriend, give them a Dutch oven, and they'll be satisfied with you. Okay, now. Never expected that answer. A lot of people don't have expectations of me, so I might as well fill in the gap of the unexpected. Hey, listen, that's all you need in your life. A little bit of, please, please take me as your disciple. Oh man, you're already my disciple, Planet. See, you're in my class. There you go. You can ask the sagely one for any advice. Though I'm definitely not too sagely. I just try and offer advice if I can. Let's see. What's a good piece of advice? Man, I'm trying to think. Hmm. Yeah. Don't smoke. Don't hotbox before you have to come to class. That's the that's my advice there. Never hotbox before coming to class. Perfect. Hi, Rohan. How are you? That's. I had a student do that once, and yeah, you could smell that from about 20 feet away. Oh man, it was bad. Anywho, yeah, we're gonna do polynomial division. I promise you that. It's true. The laziest way, the best way, as long as it's consistent. Efficiency at its finest. All right, you gotta do stuff. At some point, I gotta do stuff. Let me get around to doing things. Hey, Rohan, if you're still in here, how you doing today, buddy? Just asking. All right, so what we're going to do here first is use the leading coefficient test. So the leading coefficient is equal to 1, okay? What is the degree of this polynomial? What's the degree of this polynomial? 4. Say 4. Good, my friend. I hope you're having a very wonderful day, wherever you are. Okay, so we have an even degree and a leading coefficient of 1. So, based on those two things, what is the end behavior of the graph? What do we say there in our rules? The graph looks nice. There you go. But I'm looking for the end part of the graph there using the leading coefficient test. Going up. All right, good. That's correct. So the end behavior here specifically is, again, we're going to basically set our expectations here. That's right, yes. So the end behavior is that we are going up on both ends. Okay, so we have a really good idea. We know what it looks like here. Again, it's like a big U. All right, so just like so, or actually I'll just draw it in just for ease of use. Okay, so again, it's going to look like this, where it kind of goes up, blah, blah, blah graph, and then up like that. Okay. All right. So this is our expectation. Whatever's going to happen on the calculator is whatever happens on the calculator. Great. But we at least know that by generality, that's what it's going to look like. Okay. Let's look at the next part here. We got to determine the zeros and their multiplicities. Okay. At this moment in time, we don't know what the zeros are because, as you can see here in this polynomial, we haven't factored it quite yet. So, let's go ahead and see if we can factor this first before we determine what the zero and their multiplicities are going to be. Alrighty. Okay, so what should we factor out first? Sounds like a good idea here. What do you think we could factor out here? All right, x squared is correct. Good. That's right. So here we're going to get x squared. All right. So we got that. Oh, I was about to not hit the right key. All right, so what do we have left over if we hit x squared there? What happens when we take out an x squared? What do we got left over? All right, very good. All right, so if we take out that x squared, we have 2 squares left over. That's right, x squared minus 6x, all right, plus 9. Right. Okay, so far so good. Now we can see if we can factor out this part here, the x squared minus 6x plus 9. Okay, so let's go ahead and do that. And so if we factor both of these, if we factor this, x squared minus 6x plus 9, and the x squared for sure, absolutely. What does that factor to? X squared minus 6x plus 9. What's that going to be? Actually, I'll just need one of these. All right, x minus 3, or x minus 3 squared. Absolutely right. Excellent. All right, so x minus 3 times x minus 3. When factoring, do you add up the powers? Yeah, so basically I just kind of, actually more like subtract the powers. So I took away 2 from the x to the 4th, I took away 2 from the x to the 3rd, and I took away 2 from the x squared. So when you factor, you're actually subtracting out powers there. Oh, whoops. And then we get this. Okay, so let's take a look here and what we ended up with. So after everything's said and done, all right, after everything's said and done, this is what we have here. All right. Okay, so not too bad to get to our, result that we wanted to get there. So, pretty nice and straightforward. Hey, that's okay. That's what we're here to do. We're here. I'm here to help. This isn't a competition. It's about learning. That's about it. Doesn't need to be anything harder than that. All right. So let's find the zeros of this polynomial. So let's go ahead and put this down here. Oops. So what are the zeros here again? Zeros here are, oh, okay. I missed that part. So the zeros are 0 and 3, right? So we can see here, right, 0 and 3. We got 0 here from the x squared and 3 here from the x minus 3. Okay, so far so good. Okay, now we need to determine the multiplicity of each of these. So what is the multiplicity of 0? All right, the multiplicity is 2. Good. All right, very nice. And what's the multiplicity of 3? All right, 2 as well, correct. Okay, so they both have the same multiplicity. So we have the expectation here to pretty much say, all right, it's going to touch at those 2 particular zeros and then kind of go back up. And it could do anything else, it could do, kind of whatever below that or in between. It'll go up and down, whatever. But that we know for a fact of what the behavior is going to be since we have the even multiplicity here at those zeros. All right. Now, Next, we're going to go ahead and use our calculator here to find additional points such as maximum and minimum points. So there are kind of a couple ways to do this here, but if you have your graphing calculator here, let's go ahead and showcase how we can do that here on the graphing calculator. I'll also show you here on the computer as well, if you're going to use the computer here. But I want to at least showcase a little bit of the graphing calculator here. And yeah, wow, this is actually kind of bad. So, okay. All right. Turn on the light here. All right. Well, we're gonna see if we're where we're going here. So, okay. So, first things first here on your calculator here we're gonna go ahead and hit we're gonna hit y equals. Yeah, but we're not in calculus. You can differentiate with respect to x. Yes, you can. Yes, you can. Um, not that tough to do that. Okay, and we're going to go ahead and put in the equation here. So the original problem. So x to the fourth minus 6x cubed plus 9x squared. Okay, and we're going to go ahead and hit graph here. And you may see on your calculator, you may see it as a shape of a W. Okay, kind of a shape of a W there. And you see it how it kind of touches at 0 and then goes back up, kind of goes up again, kind of comes back down, touches, and then there you go. At your school, this kind of calculator were forbidden. I know. Welcome to the system, my friend. Honestly speaking, though, I understand why they would want to forbid it, but at the same time, I kind of feel that it's kind of pointless a little bit, only because of the fact that in the real world you're probably using this thing anyway, or you're using a much more sophisticated computer program. So, just saying, pretty much. It's just basically the sign of the times. So the more you rely on, the more you have the electronic technology, as much as old school as I am, I understand that the realistic concern is like, oh, I'm going to use this anyway. So yeah, it's still worth it. Okay, now what we're going to do here is we're going to draw this graph using this calculator here. Okay, yes, the graph is definitely a W. That part is definitely true. Now, what we're going to do is we're going to figure out what the top of that W is going to be, that little hill part there in the middle of the W. Okay, and so for us to find, yeah, that's right, you do. All right. Yeah, I agree. Conventional way is sometimes the best way, as long as you have the fundamentals. We're gonna basically the middle part of the W, the not the ends, but the middle part. So we see we have kind of that vertex there, and we want to determine what that vertex there, that maximum point, kind of is. Okay. So what we're going to do here is we're going to hit the second key and the trace key. So hit the second key and the trace key, and you should get to this calculate menu that I'm going to show up here on my camera as best as I can. Man, your head's in the gutter today. Completely in the gutter. All right. Okay, so as you can see there, you have those calculate functions. Now we're going to go down to number 4, which is maximum. Okay, so go down to number 4, which says maximum. And on your screen there at the very bottom, it'll say left bound. Okay, that's fine if it says left bound. We're going to do something here today. Not today, sorry, man. So what we want to do is we want to pick a point that's to the left of that maximum. So I'm gonna kind of zoom in here just a bit, kind of show that off on the screen. I'm gonna pick that point right there. I know I need to kind of move that down. There we go. So you can kind of see it. I know it's not the greatest thing here, but you can kind of see where the cursor is kind of blinking. That's to the left of that maximum point, because I don't know exactly where it is, but I'm going to let the calculator tell me. And I'm going to hit enter. Anytime now. Okay. Oh, sorry. Messed that up. Do that again. There we go. Then the next thing it'll say right bound. Okay, so it'll say right bound next on the calculator at the bottom of the screen. So we're going to go to the right of that maximum point, and we're going to just scroll over. Okay, so I just kind of picked a spot here to the right of that maximum. Okay, just like so. And we're going to go ahead and hit enter there. And then the next thing that you'll see there is the word guess. Okay, once it says guess, just hit enter again, and then it'll tell you what your maximum is going to be. Okay, very good. So if you did this right, you should be given a point here in x comma y coordinates. So that x comma y coordinates here is going to be x is going to equal 1.5, and then y here is exactly as you stated there, JTS, 5.0625. So that'll be y. And those are your coordinates there of where your maximum is going to be. That little local maximum is going to be in that case. Okay, so if we want to now draw a graph, yeah, I mean, it's not going to be a super exact science here. So if you did it by hand, it's not going to be a super exact science. You know, you're not going to round to 5 because it's not exactly 5, but you're going to just put it like a shade above 5. So if you did it by hand, then you can't do much about it because you were not doing something that's super exact. If it's on the computer, that's a totally different story. That'll do it for you, and it's in your stead. So that's not too hard to figure out. But you can see here, at least for the graph, if I were to just draw it out by hand specifically, it'll confirm everything that we've kind of talked about here. So basically, at the end of the day, it'll look like this. So we have our graph, like so. We have 0, 0 right here in the middle. We have 1, 2, 3, another 0. And we have our point there, which is 1.5 and 5.06. So put 1, 2, 3, 4, 5. And so we'll have 1.5, which is right about there, and 5.06, which is kind of right about there-ish. And now that we have the idea about what the end behavior of the graph looks like, and we know exactly how this will be drawn out, so it comes down, it touches 0, goes back up, touches our mini vertex, comes back down, touches again, and then comes back up again. All right, and there we go. We've effectively went ahead and found our graph. Now that's using the calculator. The W, yes, fly the W, indeed. That's a Chicago reference. Okay, now if we want to do it on the PC here, there is a nice little program that kind of helps a bit. So there is a Symbolab. And so if you go to symbolab.com, you can actually just type in like graphing this function here. So I'll go ahead and just type it in real quick. Oops, that should probably be small x, but okay. Okay, so let's say this is our function here. So then I click on the graph here, And then as you can see, this has the major points here. So if you go up here, this will give you the exact value, all right away. And you can see exactly models exactly what we have just done here. Okay, so there we go. You have a calculator as a resource there, and the PC kind of helps too. So there you go. Good beans. All right, questions about that? No? Okay. Just looking at some other examples there. Okay. Okay. Let's go ahead and take a look here at the next one here. All right. So we're gonna take a look here at the next handout. All right. Since we're done with section 3.2 here, so I'll bring over 3.3 and 3.4. There we go. All right. So in this section here, in section 3.3, we're going to be talking about long division and synthetic division. All right, the things. All right, let's do the things. Okay. So how are we going to do long division? How do we do long division with polynomials, and what are some things to remember? Okay. So what we're going to do here is we're going to do an example right away, and we're just going to plow through this example here, and we'll make some notes here, of course, in this little box. So there are certainly some notes to make, okay, when we go through with it. So let's take a look here at an example. Okay, now what we're going to do here for this example is we're going to basically, essentially, we're just going to do the same thing as regular long division. Okay, so do the same thing as regular long division with the remainder as well. So we're going to take a remainder here. So we are going to do the same thing as regular long division, including the remainder. And we'll see how this works here for long division of polynomials. All right. Okay. So let's go ahead and, yeah, you know what? I'll just make up one. Why not? Sure. Okay. Okay, we'll divide that by. Okay, there we go. So here we have 3x to the fourth minus 2x to the third plus 10x squared minus x plus 5. And we're going to divide that all over x minus 2. Okay. Alrighty. Okay, so how do we do the long division with this? Well, let's just put, again, our divisor here on the outside, x minus 2. And we'll put this whole polynomial here on the inside. Okay, there we go. All right, now all we have to do here is pretty much ask the same question over and over again. Now, if we see this x out here, this is going to be our linchpin right here, okay? We need to determine basically what times whatever x we have on the outside is going to equal 3x to the fourth. Okay, so what times x equals 3x to the fourth? Three x cubed, that's correct. So I'm going to write 3x to the third up here. Okay. So what we're going to do next is, what we're going to do next is we're going to take that 3x to the third, okay, and we're going to multiply it by x minus 2. So let's put that as a side step here. So we have 3x to the third and x minus 2. So we're going to get here 3x to the third times x is 3x to the fourth. That's what we're looking for. And 3x to the third times negative 2 is minus 6x to the third. Okay, now the next thing that we have to remember here, and what will certainly be put here, is the next step. The next step here specifically is going to be subtracting each time down. So just like regular division, okay, we're subtracting each time down. So let me put that as a note here. All right, so note, we're subtracting each time down. Okay, and bringing over the next term or terms. Okay, so let's take a look at what that means. In this case, all we need to do is change the sign of each. So we're going to go ahead and do that right now. So we're going to have minus 3x to the fourth if we change that sign, and plus 6x to the third if we change that sign. So what happens here is what should happen is that this 3x to the fourth should cancel out. We say goodbye to that. We have minus 2x to the third plus 6x to the third. So that's going to be 4x to the third. And then we'll bring down this plus 10x squared. Okay, now we answer the question again. What times x equals, and now in this case, 4x to the third? What times x is equal to 4x to the third? 4x squared. Good. That's right. 4x squared. All right, so we're going to do our next part here. So again, just putting it off to the side here, we get 4x squared times x minus 2. That'll be written on our next line down. So what we have here specifically is going to be 4x to the third, which is what we're looking for. We have 4x squared times negative 2, so that's minus 8x squared. Okay. Now we're going to just change the sign because we're subtracting. So we change the signs of each. So what we have happen here is this cancels out like it's supposed to. Next we have 18x squared. And we'll bring down the minus x here. All right. So far so good. Okay. What's next here? Again, next here is we have to multiply x by something to get 18x squared. What's that going to be? $18x. Very nice. That's correct. So we get 18x. Okay. So now we just multiply here again. So again, same thing. All right, so here we have 18x times x, which is 18x squared, and 18x times negative 2, which is negative 36x. We will flip the signs here once again. So it's minus and plus. So the 18x squareds, they'll cancel out. Minus 1 plus 36 is 35x. That will bring down the 5. Okay. Why do we flip the signs? Because we have to subtract each time down, just like regular division. That's why we have to flip the signs. So like you do in regular division where you just like, okay, I take this number minus this number. Well, we're now doing the same thing, only with polynomials as opposed to just regular numbers. In either case, again, you flip that sign. So that's why you're just doing it kind of the plain old-fashioned way of how you kind of did it before way back when. That's right. So if you notice here what I did, JTS, if you notice what I did here for the problem, notice I put it in black about where I flipped the signs here. So this was originally positive 3x to the fourth, but that became minus 3x to the fourth. This was originally minus 6x to the third, but then that became plus 6x to the third to note the sign change. Oh, all right. Okay. Okay. So here in this case we have 35x, and in this instance we're going to add 35. So then this last part here will be 35 times x minus 2. So we have 35x minus 70. All right. Okay, so now what does this become? This becomes minus and this becomes plus. So we get 75 here. Now, 75 is the remainder here for this particular problem anyway. 75 is definitely the remainder here. However, I want to point out one very important thing, okay? And that is you need to write the answer here in a very particular way, okay? So I'm going to just go ahead and write this out on the sheet of paper now, back on our Word document here. Oh, wrong one. The other one. There we go. So a couple of things to remember how we do long division, all right? And this is going to happen for, well, this is not even for long division, it's also for synthetic division as well. But specifically, all right, so again, a big note here. This one will get a bold. So note, you must write your answer in a particular way. All right, that particular way is the first thing you'll have is the answer function. All right, and then you'll have plus you're going to have r of x, which is the remainder function, divided by the divisor function, which is d of x. Okay, so a of x is equal to, a of x is the answer function. R of x is the remainder function. Okay, and d of x is the divisor function. Okay, so in this particular example, what exactly does that look like? That's kind of the key thing here. What exactly does that look like? Well, let's take a look at our answer here. So we're going to have this whole entire answer here. Okay, so the final answer here. So the final answer here is going to be 3x to the third plus 4x squared plus 18x plus 35. So that part there is just the answer part. Then, since we have a remainder here of 75, we're going to do plus 75 over what we divided by here, the divisor, which is x minus 2. Okay, and that is going to be our final answer for this problem. Okay, any questions? No? Okay. All right. Of course, there's a shorter way. Well, kinda. Um, kinda. We need to talk about that here. Yes, there is a lazier way. However, there are limitations to doing it the lazier way, which I have to do right now. Okay. There are a couple more things though that absolutely do need to be said here. First and foremost, something that we will be using here quite extensively in this section is going to be every. This is actually really important here. A key point for this one, because this is often forgotten, so hence why I put it as a key point. All powers must be represented. So what do I mean by that? By all powers must be represented, even in a synthetic division or in long division, all powers have to be represented. So meaning to say, let's say you had let's just go back to our example here. Let's say I had this, and I'll erase this here. Oop. All right. So let's say I had x squared minus 5, okay, and I divided that by x plus 1. All right, I'm not going to do this division here, but what you need to understand is that even though I skipped a term, okay, I put x minus 1 on the outside, that part is true, but on the inside I have to put in the representation for x. Even though you skipped it, there's still no x's, but that still needs its own column at the same time. So we have x squared plus 0x minus 5. Okay, so that's kind of the proper way of writing that out. This is really important, not also for long division, but for synthetic division as well. So we'll be using this sometimes. So if you see them kind of skip stuff around, you know that you'll need to put a 0 in those places. So please be very careful when reading the problem. Okay. All right. I'm going to put one last note here, is that you must do long division if you are dividing by a degree 2 or more polynomial. Okay, so if you have, say, x squared plus 2x minus 5, if you're dividing by that, well, you'll have to do long division. You're not given a choice in the matter. Okay. All right, any questions about that before we move on? No. Okay, good. Okay, let's look at the next one here. Number 2. What are the rules you need to follow to do synthetic division? So as all of you asked, what's the lazier way? Well, here you go. You got the lazier way in synthetic division. However, there are rules definitely to follow here about when we can use synthetic division. So we're kind of limited, unfortunately, in terms of when we can use this, but in most cases, in many cases, what we'll look at here, we'll be able to use it without too much trouble. All right. So the rules here specifically are going to be, let's list off the rules here. Number 1, you can only use synthetic division if you are dividing by x plus a or x minus a. All right, so if you're dividing by x minus 1 or x plus 2, okay. All right, so you can certainly get away with doing synthetic division so long as it's a single, kind of like something looks something similar to that. Even 2x plus 1 will work, that's fine. But as long as it looks something like that, that's okay. Again, a is any number. All right. I guess I should put where a is any number. Okay. All right. Next, number 2. What we're going to have here is we're going to have an outside and inside area. So we're going to have numbers. We're going to have a number on the outside, and we're going to have a number on the inside. Numbers on the inside. So let's look at number 2 here. Why is it doing that? All right, let me 16. Okay. The number on the outside will be opposite of the number you are dividing by. Okay, I'll describe what that means momentarily, but it'll be opposite of the number that you're dividing by. Let's look at number 3. Number 3, the numbers on the inside are the coefficients for each power. Okay, so each of the coefficients, so all those numbers in front of the letters, okay, all of them will be taken into account. Number 4 is what I've already stated before, okay, and again, just to say again, all powers must be represented. Okay, so if you skip, you got to put a 0 there. That still counts. Let's go to rule number 5 here. Rule number 5 is you need to bring the first number on the inside down. Okay, and then multiply that number, and then multiply that number to the number on the outside. Put the result of rule 5 in the next column over. All right. Number 7, this is very important here. Number 7. Number 7 is, unlike what you did for regular division where we subtracted each time going down, okay, very important here, we have to add straight down. Add straight down. So we are not subtracting here in this case, we are actually adding here in this case. And then rule number 8 here, again, repeat repeat steps 6 and 7, or rules 6 and 7, until you reach the end. All right. So we have all that stuff there. That's all well and good. No, sorry about that. Okay. So we have those 8 things are the rules associated with synthetic division. Obviously, it seems like a lot. In reality, it's actually rather short. But there's a lot of kind of small technicalities that I wanted to go over at the very least, so you could see it in action without having to be overwhelmed. So let's take a look here at an example. I'll make up a random one, and we're going to go ahead and see how synthetic division works. All right. Okay, so let me go ahead and make up a problem. So let's go with okay. Okay. Oh, sorry about that. Yeah, of course. Apologies about that, JTS. Hopefully that'll be a little bit more helpful so you can write that down. Just let me know when you got it. So, all good? Perfect. All right. Excellent. So I'm going to go back to the paint tool there. Okay. So what we're going to do first is we're going to have one number on the outside and the coefficients here on the inside. So to kind of section them off here, we're going to draw a little bar here. Numbers to the right are going to be on the inside. Number on the outside is going to be on the left. So let's go back to your rules here. You can reference them now if you have them written down. It's that we're going to take the opposite of the number here that we're dividing by. So if you see here, we're actually having x plus 4. So we want to take the opposite of that. The opposite of plus 4 will be minus 4 here on the outside. Okay, so that is what we're putting here on the outside based on the rule that we had from before. Okay, now the next question here is, what are the coefficients here in this case? So what are the coefficients that we see here in this instance? What are my coefficients? What are the numbers that we're going to put here? Three minus 2, 5 minus 3, and 7. That's very close. Very close, Gerda. We're missing something here. Zero, 3. Not quite 0, 3 there. Not in that order anyway. A zero's in there for sure. Plus 4? No, definitely not plus 4. We always take the opposite of this number here. So that's why that's minus 4. So our first coefficient here is 3. Right. Very good, Phantom. Right. I'm just asking for these numbers here to the right of this bar. Those coefficients, those numbers in front of these powers. You almost had it right, but you forgot the 0. Reason why we have 0 is it goes 3x to the 5th to 2x to the 3rd. Problem is that we skipped the x to the 4th, but since every power must be represented, then I have to include those as well. Okay? Yeah. So we have the number on the outside and the numbers here on the inside. Now, the first thing that we're going to do here is we're going to bring down this very first number of 3. This automatically happens by default in every one of these problems. Okay, so you don't have to worry. Whatever this first number is, just bring it down. We'll keep moving forward. All right, next here we have 3 times minus 4. So we're going to multiply here this 3 times the minus 4. 3 times minus 4 is minus 12, which we now will put in the next subsequent column. So just like so. Now, as was stated here before, let's go back here for just a second. Okay. Again, we are going to add straight down, right? That's the key here. We're going to add straight down. So if we have 0 plus negative 12, that's going to be minus 12. Okay, we're going to put that just like so. All right, now we just repeat this process here. So we have minus 4 times minus 12, which is positive 48. Here we have minus 2 plus 48, so that's going to be 46. Next we have minus 4 times 46, so that's going to be negative 184. Okay, we add these together here. 5 and 184 is minus 179. All right, I'm not sure what that is off the top of my head, but we'll find out. So this is 716. Adding these together, we get 713. I know the numbers are pretty ludicrous, but that's okay. And then we're going to get, we get minus 713 times negative 4 is going to be, I wonder why I did that. All right, this is going to be minus 2,852. And we'll add that to 7. All right, so minus 2845. Okay, and then what we're going to do here at the end, even though these numbers are very silly, you could actually organize your answer here more appropriately. So what we're going to do here for this very last number you see here, this minus 2845, we're going to put a little box around it just like so. Okay, so we'll put a little box around that. All right, and you'll see why in just a second. Okay, now why am I putting a box around that specifically? It's because if we go back to our Word document here regarding synthetic division, one of the things that we need to discuss here in specifically is that with synthetic division, all right, so again, a note here regarding synthetic division, the answer is always 1 degree less, I guess I'll put that less than what you started with. Okay, so no matter what degree you start with, you're just going to bump it down 1 degree. Okay, so what does that mean in the context of the problem? In the problem here, since we started off with 3x to the 5th, we bump it down by 1 from a degree 5 to a degree 4. So this essentially, this first 3 here you see, is going to be our x to the 4th. This will be our x to the 3rd. This is going to be our x squared. This is our x terms. This is our number. And then this last one here is your remainder. And that's why we went ahead and put it in a box, just like that. So in this instance, our final result is going to be 3x to the 4th minus 12x to the third plus 46x squared minus 179x plus 713 oops, minus 2845 over x plus 4 as our remainder. And there we go. We got our final answer using synthetic division. So you can see how fast that went, much faster than long division. I'm sure that if you did this random problem I came up with, it would take you a very long time to do. Questions? Okay. Again, type no in chat if there are no questions. If you do have a question, please type that. Okay, yeah, I can go back to the rules. Sure. There you are. Let me make that a bit bigger. All right. All right. Got a few more to go here, but, well, actually, I should say a lot more to go, but hey, I figured we'd get through about half of this today. So, all right. We're going to do this last two questions here because number 5 is going to take me quite a while to do. So that question there, number 5, is going to take me, number 5 and number 7 are going to take me a while. So, boo. It's at least a 20-minute problem. All right. But 3 and 4, very simple. Let's look at what is the remainder theorem. All right, so that's the next question here. What is the remainder theorem? So the remainder theorem here is actually one of the most straightforward theorems that you're going to find. Essentially, at the end of the day, is if you divide a polynomial by x minus a, then f of a is going to equal to the remainder of the polynomial after doing synthetic division. Okay, so there is a second purpose why I put the box around that last number. Let me go ahead and show that off here. Okay. So I'm going to go ahead and do this. Go back to our guy here. Okay, so this is our problem right here. Okay, we just finished it. Now here's my contention. Okay, my contention is fairly simple. We took minus 4 as our outside number. My contention is if I do f of minus 4 in the original function, that somehow, some way, that's going to equal minus 2,845. Okay, because that's the remainder there. So if I plug in minus 4 in for every x in f of x, for the numerator here, the very top, then I should get that answer. So let's go ahead and give it a shot here. Okay, let's see what happens. Okay, does that actually happen? So we have 3 times negative 4 to the 5th minus 2 times negative 4 to the 3rd plus 5 times negative 4 squared. Wow, Joe Jakes at the 25 cheer, man. Thank you. I really appreciate that. Wow, I didn't deserve that. Man, I feel bad. Thank you very much. I much appreciate it. So if you put this in your calculator here, go ahead and give this a try. Oh. Man, another 25 bits? Man, you don't have to do that. Math is cool. Math is fun. Math is fun when you want to make it fun. I will say that. That's definitely true. Math is definitely fun. Thank you again. It's very, very kind of you. You don't need to do that, though. I mean, I just hope you just learn something and just have fun. That's about it. So, do you guys try this out on the calculator here? Did you guys get the answer that we're looking for? Did we get minus 2845? Oh, well, it'd be helpful if I actually put it on the screen. There we go. Yes? All right. So think of it this way. As ludicrous as the number minus 2845 is, you can see that it does hold consistently when we plugged in minus 4 into a calculator into this original function. So that's the power of the remainder theorem there. Okay? That's the power of the remainder theorem in that case. Now, we're going to use this remainder theorem in the next question. So we've confirmed that this definitely works. But how is this going to help us into other topics here when it comes to doing polynomials? Let's go ahead and see what we get here. So let's look at this last question today here, because that last question is going to take me a long time next class. What is the factor theorem? Okay, so what is the factor theorem? So basically, what is the factor theorem here? The factor theorem basically says is if, let's make that bigger. That's kind of a thing here. This is actually really important. It says if A is a zero of a polynomial, then f of A equals 0, which implies that the remainder after doing synthetic division, or after doing division, should also be 0. Okay? So if we want to find our 0 and we want to confirm that it's a 0, our remainder should be 0 if we do the synthetic division out. So we know that if we plug it in the function we get 0, that's fine. But this also works for synthetic division since the remainder theorem also holds true. So now we can link that together and essentially take a shortcut into finding zeros because of that fact. Are there any questions about that? So basically put, what we're going to be doing here next time is that's really nice, Team Solo, but you're going on a timeout if you want to timeout for you. All right, moving on. All right, so what we're going to be doing here next time is we're going to be specifically looking at a way to narrow down our choices to find zeros of polynomials and using the factor theorem in order to go ahead and confirm whether or not that's true. So one thing that we're going to need for next week here, next Tuesday, is you're going to need your calculator for that section. So we're going to do a lot of stuff here with the calculator. So for the remainder of these questions and for the next section as well. So be sure that you have the graphing calculator with you for next time. Okay? All right, any questions about that? No? All right. Good stuff, everybody. Great work today. Really like the positive progress. All right. Definitely definitely very happy about where you guys where the progress you guys have made so far. All right, so we're on a good pace. We're on a really good pace, actually, really good pace. So we're actually a little bit further ahead than I probably anticipated, but you know what? That's perfectly fine. Um, can you? Oh yeah, sure, of course. Sorry about that, Planet. Here you go, buddy. So again, I'm just a little blah, 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 blah. Just to let you guys know, it may be a little bit tough to contact me here this weekend. I'm gonna be out of town for the weekend, so it may take me a little bit more time to answer your emails if you have any. I'm gonna be in Dallas this weekend, so should you have any questions, again, you can still feel free to email me. That's perfectly fine, but it just may take me more time. That's all. You good? Cool. Awesome. All right. Great job, everybody. All right. Thank you again, everybody, for coming out to the stream here today. I really appreciate your time. Uh, I really appreciate the effort you guys have put in so far. You guys have done really well. Um, so I'm looking forward to seeing the test there. Hopefully, you guys do really well. Thank you very much. I really appreciate that. Um, and thank you. I appreciate that, JTS, very much. It's very kind. And I hope that you guys have a very wonderful weekend as well, just to get a chance to relax, chill. Make sure you finish that test before then, okay? Make sure you finish your test before the weekend's up. All right? I know you guys have been doing well. You guys have been coming out every time, so I'm pretty sure. Hopefully, you've been learning through these live lectures here. Um, like I said, it's better than Zoom. So, at least in my opinion, I think Twitch is better than Zoom. That's my opinion anyway. I know some people prefer the Zoom, but I'm like, yeah, Zoom, meh. Nah, Twitch is too fun. So, all right, guys, time for me to log off. Unless there's a question, I bid you adieu. Have a great one, and we will see you later. Yeah, good night. Good night and good afternoon. All right, take it easy, everybody. All right, bye.